A deep dive into scikit-learn's Gaussian Process Regressor. The Gaussian Process Regressor in scikit-learn sklearn is a powerful tool for nonlinear regression. Using Gaussian processes, it offers a probabilistic approach to model data, providing not only predictions but also uncertainty estimates for those predictions. Let's explore its intricacies. 1. The essence of Gaussian processes. Gaussian processes are a fundamental concept in machine learning, particularly for regression and probabilistic modeling. Imagine a function, but instead of knowing its exact values, you have a probability distribution over its possible values at each input point. This distribution is a Gaussian normal distribution, and the collection of these distributions for all possible input points constitutes a Gaussian process. 2. Key components of Gaussian Process Regressor. The Gaussian Process Regressor in scikit-learn is built upon the following key components. Kernel function. This function defines the covariance between any two input points, reflecting how similar their corresponding function values are likely to be. Popular choices include RBF. Kernel radial basis function assumes similarity decreases exponentially with distance. Matern. Kernel offers flexibility in smoothness assumptions. Linear. Kernel assumes a linear relationship between input and output. Polynomial. Kernel captures polynomial relationships between input and output. Constant. Kernel assumes a constant mean function. Mean function alpha represents the expected value of the function at each input point, often set to 0 for simplicity. Noise level. Noise accounts for inherent noise in the data. This parameter controls the variance of the assumed noise distribution. Optimizer. This determines the best parameters for the kernel function based on pay. Training data. Popular choices include FMINLBFGSB and FMINC-OBILA. 3. How it works. The magic of Bayesian inference. The Gaussian Process Regressor leverages Bayesian inference to make predictions. This means, the prior belief about the underlying function is encoded through the kernel and mean function. Likelihood. The likelihood of observing the training data given the function is calculated posterior by combining the prior and likelihood. We obtain the posterior distribution of the function, which encapsulates our updated belief after seeing the training data. 4. Predictions and uncertainty estimates. When making predictions for new input points, the Gaussian Process Regressor provides predictive mean, the most likely value of the function at the new input point. Predictive variance quantifies the uncertainty in the prediction, reflecting the potential spread of values. This is crucial for understanding the reliability of predictions. 5. Advantages of Gaussian Process Regressor. Nonlinear modeling captures complex relationships between input and output. Probabilistic predictions provides uncertainty estimates, enhancing decision-making. Smoothness control offers flexibility in specifying the smoothness of the learned function. Data-driven learns the relationship from the training data without strong assumptions. 6. Limitations of Gaussian Process Regressor. Computational cost. Training and predicting can be computationally expensive for large datasets. Kernel selection. Choosing the appropriate kernel is critical and can require domain expertise. Overfitting. If the kernel is too flexible, the model might overfit the training data. 7. Tuning and optimizing. Tuning the hyperparameters, e.g., kernel parameters. Noise level is crucial for maximizing performance. This can be done through grid search, evaluating the model with different parameter combinations. Random search, randomly sampling parameter combinations. Bayesian optimization, efficiently exploring the parameter space by incorporating prior knowledge. 8. Key values in YAML configuration. Let's analyze common key-value pairs often used in YAML configurations for Gaussian process regressor. Kernel defines the type of kernel used for covariance. For example, YAML kernel, RBF kernel with length scale 1.0, RBF length scale 1.0, or a combination of kernels, RBF constant, length scale 1.0, constant value 0.5. Alpha specifies the mean function, often set to 0, indicating no prior knowledge about the mean. YAML alpha 0.0. Optimizer selects the optimization algorithm for finding the best kernel parameters. YAML optimizer FMINLBFGSB. N restarts optimizer controls the number of random restarts for the optimizer. Increasing this value may improve the chances of finding a global optimum. YAML N restarts optimizer 10. Noise sets the noise level for the data. YAML noise 0.1. Random state controls the randomness in the optimization process. Setting a value ensures reproducible results. YAML random state 42. 9. Applications. Gaussian process regressor is widely used in various fields. Machine learning modeling complex nonlinear relationships. Robotics control and trajectory planning. Finance predictive modeling for asset prices. Environmental science modeling environmental processes. Material science predicting material properties. 10. Conclusion. The Gaussian process regressor is a powerful tool for nonlinear regression with probabilistic predictions. By carefully choosing the kernel, mean function, and optimizer, and by tuning the hyperparameters, you can leverage its capabilities for a wide range of applications. Its ability to capture complex relationships and provide uncertainty estimates makes it a valuable asset in many domains.